Okay, so let's say that we have a loop, a rectangular loop of dimensions W and L, and we're going to move this loop into a uniform magnetic field that's pointing everywhere into the page. So here's the magnetic field. It's a localized magnetic field, uniform, and its magnitude is B naught. And we're going to move this loop into the magnetic field at a constant speed, V naught. So if we make another drawing of this, here's our uniform magnetic field pointing into the page. And once the loop starts to enter the magnetic field, it will look something like, let's draw it here, something like this, where part of the loop is in the magnetic field and the other part still hasn't entered the field. So this side is W and this is L, and we're moving in here at speed V naught. Clearly the magnetic flux here is 0, and then suddenly the magnetic flux starts to increase because the loop enters the magnetic field, and so there's an EMF, right, given by the fact that EMF is minus the time derivative of the magnetic flux, and the magnetic flux, right, we integrate the magnetic field over the area of the loop, so this area here, and so at t equals 0, we just start to enter the field, let's say. So at t greater than 0, we have an increase in the flux through this area, and so the normal to the surface, let's say, is outward this way in the magnetic field. Let's just say the normal to the surface is inward, is inward. So it's into the page, aligned with the magnetic field. And so when we do this calculation, what's changing is this area here, right? The area is increasing. First, there's no area that has any flux, and then that area starts to increase, and the most that it can be is W times L when the entire rectangular loop is inside the field. So this looks like B naught times W times the amount of this that's inside of the field, right? So that's the area, right? This area is increasing as more and more of this is coming into the field. So this side is W, but the question is, what's this side? Well, at t equals 0, we start to enter the field, and we enter at a rate that depends on the speed, and so this could be a distance given by V naught times t. That's the rate at which this side is increasing. It increases linearly because we're moving the loop at a constant speed V naught, so that side is V naught t, and that's the flux. It's clearly changing with time, and so when we look at the EMF, or let's say the magnitude of the EMF, forget the minus sign, let's just take the time derivative, we'll get B naught W V naught, so there's clearly an EMF. And now the question is, what's the direction? Let's find the direction of the induced current. So we're not concerned with the magnitude. We could easily find the magnitude by assuming Ohm's law and then dividing by a given resistance for the loop, dividing the EMF by the resistance and getting the magnitude of the induced current. But here we care about the direction of the induced current, and we know that the induced current generates a field, an induced field that has to be pointing in this region, it has to be pointing into the page to attempt to counter the increased magnetic flux through this region as a result of the motion of the loop into the blue magnetic field. And so we have induced red magnetic field that's that has the opposite direction there. And so by the right-hand rule applied to the Biot-Savart law, remember that the magnetic field is proportional to I dl cross r by the Biot-Savart law. And so is this going to be a counterclockwise or clockwise induced red current? And the answer is by the right-hand rule. Let's say that we're over here. We want to figure this out, and we just assume that the current is flowing that way. Then we put our hat towards the inside in this region. And in fact, we get a field that's pointing out of the page. And so we know that we want our induced current to flow counterclockwise here in order to produce a field in here that is out of the loop. Of course, the field has to circle around, so the induced field out here will be pointing in this direction because it circles around.